My name is Catalina, and I'll be presenting our work on Explainable AI for automated user-specific feedback in surgical skill acquisition. Over 300 million surgical procedures are performed worldwide every year. With growing waiting lists and demands on surgical capacity, there's an urgent need for tools that can help improve efficiency, safety, and outcomes. Artificial intelligence has transformative potential across the entire surgical pathway, from preoperative surgical care, the intraoperative period, and postoperative monitoring. To improve patient outcomes, it's not only about surgical procedures themselves, it also includes better access to surgery, optimization of surgical system inefficiencies, and improved surgical education, which includes training and coaching of surgical residents. Currently, surgical training happens in different forms. In the operating room, where trainees receive real-time guidance from experts, in simulation environments, where experts still provide direct coaching. There are clear constraints by limited faculty time and resources. Or in offline simulations where feedback is more limited or delayed. Also, current simulation systems are often rigid. They allow structured practice, but without the flexibility to adapt to the way procedures are carried out in real-world settings. Therefore, what's needed is an analysis framework that goes beyond right or wrong judgments to explain how and why skills are performed. And this is exactly where we see the potential of AI to transform surgical training. Independent practice in simulated settings can be enhanced by introducing flexibility, personalization, and guided feedback tailored to each trainee's needs. Video-based assessment is a promising avenue to achieve these requirements. Surgical videos and simulated datasets offer rich sources for developing objective surgical assessment tools. Using computer vision, we can process these video data to assess technical skills in a way that is efficient, repeatable, and scalable. Models have already shown the ability to distinguish expert practice from novice practice. The challenge, however, is that many of these models produce black box outputs, assigning scores or tags, but without explaining why. And this is where explainable AI becomes essential to not only classify performance, but to provide transparent, interpretable feedback that trainees and educators can act upon. From a human-centered perspective, we need to ask, how does explainable AI-driven feedback affect skills, cognitive load, and perception of trainees in a simulation-based training framework for surgical practice? To address this question, we design a framework that brings together all the necessary components for conducting such a study. Let me walk you through how we set this up, starting with the algorithm for surgical skill assessment. The algorithm models the movement of the practitioner's hands and their interactions with surgical instruments. This method was implemented by previous works, and we used existing models trained on an in-house dataset of 100 open surgery simulation videos. It has two phases. The first one does object detections of the tools and 2D pose estimations of the hands. As you can see in the video, we keep track of the practitioner's hands as they're doing the simulated suturing task. Then the outputs of these object detection and 2D pose estimations are used in an action segmentation model to predict the gestures involved during suturing, which are listed below. The second phase uses the predicted surgical phases and hand tool interactions to calculate proxies of dexterity that are based on clinical relevance and good practice. These can be interpreted and acted upon to improve or change practice. And these include hand orientation, hand velocity, distance between thumb and index fingers, and are defined for each hand and gesture, and depending on the gesture, there are guidelines for control and comfort when holding the instruments or executing an action. We first collected proxy measurements with the method we just described from experts to define practice standards. The experts' data collection includes attending surgeons' demonstrations performing sutures in a simulated skin pad. These video recordings were processed by the algorithm, and we did manual gesture phase annotations for a proper definition of the proxies that are going to be used as the standards of proxy gesture pairs. We define these by aggregating proxy values over time by gesture, then averaging across all trials and experts, and finding the closest expert sample to that average. And we also saved a clip from that sample as a representative of the proxy gesture pair, which are later going to be used for display to novices. Then we conducted a user study with novices and contrasted their practice to that of experts to generate the explainable AI feedback. We had participants perform the first suturing trial and process it immediately with the algorithm to calculate the proxy gesture pair values, this time using the gesture predictions. We then contrasted these with the average expert standards to find the top 3 with the highest deviation from expert standards, as shown in this example. The feedback presentation between the 2 study sessions included a video of their self-practice, and in the AI-guided condition, there was a template for each of the top 3 pairs displayed, indicating whether they were above or below expert standards. And these were next to the representative clip from the expert, which were trimmed to only show the proxy gesture pair that needs improvement. In the traditional or control group, we did the same proxy calculation, but only showed participants the video of the expert doing a complete suture with no guidance. This is the actual feedback that one participant received for the right hand orientation during needle passing. We can see that in the AI condition, participants get explicit guidance to adjust their practice. We also explained before what it means to be above or below average based on the proxy that we are mentioning. In the traditional group, we only show the video of the expert doing one suture. I will first present the objective measurements we collected. We analyzed 24 trials from 12 medical students. We did manual gesture annotations of trials before and after the feedback intervention, and we only included in the analysis the measurements of the top 3 proxy gesture pairs that were used during the feedback presentation. The first measurements is the performance gap with respect to the experts, where improvements are defined as reducing deviations from expert standards. We noticed positive changes in the traditional feedback and negative changes or improvements, meaning that participants' practice was closer to experts in the explainable AI group, but this difference was not significant. The second measurement is the relative change of the proxy values that they were shown in the feedback because we wanted to see if they changed something in their practice. So we observed more changes in the traditional than in the explainable AI group, but these differences were not significant. There was only an actual change. However, there was only an actual change in the explainable AI group. From the subjective measurements, we learned that cognitive load and confidence improve after feedback, and usefulness ratings are not different across feedback types. A qualitative analysis also showed that participants did adjust their practice in the desired direction when they were exposed to the explainable AI feedback, as we demonstrated by these two examples where we made the participants increase the thumb to index distance and then pull the suture with the right hand. To summarize, explainable AI can provide user-specific feedback that supports more independent practice. When we measure AI-based surgical feedback as a form of human-AI interaction, we see that outcomes are comparable to groups exposed to traditional feedback. At this stage, early learners often focus on simply becoming familiar with the task, which means they may not be yet fully benefiting from these interventions. Third, careful study design is essential. Factors like the number of trials, the amount of feedback exposure, and targeting the right learners all shape the measurable effects of AI-driven feedback. Together, these findings highlight both the promise of explainable AI in surgical training and the need for thoughtful design in how we evaluate it. Thank you.